take a moment to breathe deeply. Did you know that you might have just inhaled plastic particles? Every year, we unknowingly take in hundreds of thousands of microplastic particles through the air we breathe, the food we eat, and the water we drink.
Have you ever considered what might be in your fresh salad? You could be consuming chemicals from plastics. With around 16,000 different chemicals used in plastic production, 25% of which are unregulated and potentially harmful, it is important to examine what's on our plates.
My name is Silvia Bucci, and I am a researcher at the Institute of Meteorology and Geophysics. My studies are dedicated to understanding how pollutants are introduced into the atmosphere and how they can impact the environment through atmospheric transport processes.
My name is Thilo Hoffmann. I'm professor of environmental geosciences. My research is dedicated to understanding environmental pollution and developing solutions for a sustainable future. We present this video together because our research areas complement each other. Silvia focuses on how pollutants like microplastics travel through the air, while I study their impact on soil, water, and ecosystems.
Together, we provide a fuller picture of how plastic pollution spreads and affects the environment and human health. After watching this video, you will understand both the benefits and the risks of plastic use, especially in agriculture.
You will see how plastics move through air, water, and soil, how they affect health and climate, and recognize the need for sustainable practices and systemic changes like a global plastic treaty. Plastic is a wonderful material. It is cheap, durable, and extremely versatile with thousands of applications and widespread use. It is truly a success story, and it's difficult to imagine any household without it. But also the whole medical sector would be unthinkable without plastic for items like infusion bags, syringes, or sterile packaging. However, this success comes with a significant downside: massive global plastic pollution. Today, more than 400 million tons of plastics are produced each year. This figure has grown exponentially over the years and is expected to grow exponentially in the future without a global plastic treaty. Therefore, many stakeholders argue that we need a global cap on maximum polymer production. The problem is that plastics are used all over, found in everything from packaging and construction materials, think paint, to car parts and countless other products. Often overlooked, plastics are a significant contributor to climate change. Researchers estimate that up to 3.5% of current greenhouse gas emissions come from plastic production, surpassing the emission generated by the aviation industry. Most of these emissions are not linked to oil as a fossil feedstock, plastic use, or recycling, but rather to the petrochemical production process itself. This is largely due to the reliance on coal and oil-powered energy sources for production, highlighting the critical need for a shift to renewable energy. If plastic consumption rises as projected, a recent study from Berkeley suggests that by 2026, plastic production could account for as much as 20% of global greenhouse gas emissions. But even the OECD estimates that greenhouse gas emissions from plastic will rise from 1.6 gigatons of CO2 equivalents in 2020 to 2.8 gigatons by 2040. The impact of plastics also relates to their chemical composition. Plastics contains a wide range of chemicals known as additives. They define the function and property of all plastics. There is no such thing as plastic without additives. These substances give plastics their versatility and include everything from colorants to processing aids to stabilizers, flame retardants, and many other components. It is estimated that there are over 16,000 different chemicals linked to plastics, with more than 4,200 of them considered chemicals of concern, with 15 priority groups. Approximately 3,600 are not currently regulated on a global scale. underscoring the need for improved strategies and stricter global regulatory measures. Let's see how plastic emissions are distributed globally. This chart shows the global plastic emissions in megatons per year on a country basis, with the highest emitters located in South and Southeast Asia, but also Brazil and Russia. India alone accounts for about 1/5 of global emissions. Surprisingly, Nigeria ranks as the second largest emitter worldwide, surpassing even major powers like China and Russia. Notably, China's position as only the fourth largest emitter marks a significant change, as it had consistently held the top spot for global plastics emissions in the past. However, if we look at plastic emissions per capita, it shows us a very different and unexpected picture. China and India's emissions are lower, while Russia remains a significant contributor, and the whole of Africa takes an enormous share. This is particularly concerning given forecasts that predict the most substantial increase in plastic emissions will occur in Africa. Let's dive deeper into plastic emissions and income levels. This overview across countries, categorized by the World Bank income levels, reveals a surprising trend. High-income countries contribute very little to global plastic pollution, whether measured in total tons or per capita. In these countries, plastic pollution mainly results from littering, which occurs at relatively low rates. In contrast, low-income countries struggle with uncollected waste due to inadequate waste collection systems, with nearly 50% of plastic waste being open burned. However, this does not absolve the Western world or corporations of responsibility, as they continue to export plastic goods and plastic waste despite knowing that proper collection and management are not in place. Let us now take a closer look at one specific example of plastic pollution: agriculture. Plastics in agriculture are especially interesting because, as you will see, they have both positive and negative effects. The three main ways plastics and the chemicals in them end up in your salad are through atmospheric transport, which Sylvia will explain in a minute, recycled wastewater, and the use of sewage sludge, known as biosolids. Here you can see some of the different ways in which plastic can be found in agriculture. Mulch films or irrigation pipes are part of important practices to reduce irrigation water, pesticides, and fertilizer demand. However, you can also see how plastic enters farmland through biosolids, treated wastewater, tire wear, and polymer-coated fertilizers. The challenge of plant agriculture, therefore, is to reduce its environmental impacts while increasing crop yields, adapting to climate change, and maintaining soil health. If plastics are used more sustainable in agriculture, it can support several UN Sustainable Development Goals. But plastic pollution is also harmful for agricultural ecosystems. This figure illustrates the different ways plastics can impact soil health, plant growth, and the surrounding environment. It highlights problems such as poor waste management, plastics being carried off by wind and water, fragmentation of plastics ending up in the soil or groundwater. The image also shows how plastics and their chemical additives can affect plant roots, soil quality, beneficial microorganisms in the soil, and finally, crop yield and quality. Finally, very small plastic particles might enter the food chain and end up in our body.
Plastic can really be everywhere, including the air we breathe. If you want an idea of how much is floating around you at this very moment, let's start with a simple question. Are you indoors or outside? In outdoor environments, a person can breathe around tens to hundreds of particles per day. When you are at home instead, there is a much higher concentration of sources. Just look at all the synthetic materials around you, like plastic bags, carpets, surfaces covered in paint, and even your own clothes. All these sources, combined with the limited ventilation of the closed environment, increase the likelihood of airborne plastics, potentially exposing you to thousands of particles per day through inhalation. But how does plastic end up in the air? To answer that, let's first understand how microplastics enter the environment. Some particles are intentionally produced at micrometer or nanometer scales, for industrial applications, for example, and you might also recognize them in some personal care products you have at home. However, most environmental microplastics come from the breakdown of larger plastic items, such as car tires or litter, until they are small enough to be resuspended in the atmosphere. Think of old plastic bags at home. Over time, they become brittle and fragment into smaller pieces. This degradation process affects any plastic item when exposed to sunlight, weathering factors, or mechanical stress. Plastic particles can hence be found everywhere, in the sea, over land, in rivers, or even directly emitted into the atmosphere. With time, these fragments break down even further, increasing their chances of being resuspended in the air, being redistributed all over the environment, and ultimately entering our respiratory systems. Due to the persistent nature of plastic, these particles are not readily eliminated from our bodies. Once inhaled, airborne particles can pose various health risks depending on their size, their shape, and composition. Particles between 2.5 and 10 microns generally deposit in the tracheobronchial region, where they can cause irritation and infections. Particles smaller than 2.5 micrometer can penetrate further into the respiratory system, reaching the alveoli and potentially causing inflammation and respiratory conditions. Ultrafine particles, typically under 0.1 micrometer, can even enter into the bloodstream or the lymph nodes, where they may contribute to cardiovascular issues, systemic inflammation, and increased risks of diseases, including cancer. The shape of these particles also plays a role in their health impacts. For instance, fibers from synthetic fabrics, due to their thin diameters, can be inhaled and reach deep into the respiratory system, even when they are bigger than a few micrometers. Researchers have found within lung tissue fibers up to millimeters in length. Beyond physical harm, airborne microplastics often carry biological agents like bacteria or viruses, or toxic chemicals, such as the additives Thilo mentioned just earlier, increasing in this way the health risk associated with their inhalation. Aside from the health effects, airborne microplastic also represent an environmental hazard. Among all the mediums of transport in the environment, the atmosphere is the fastest and the most efficient, allowing these particles to disperse globally. Microplastics have been found even in remote locations where minimal human activity is present, such as mountain glaciers or Arctic regions. As with any other atmospheric pollutant, these particles can be transported by winds, and especially particles smaller than a few tenths of micrometers, they can really easily travel across the globe. Once airborne, this particle can interact with cloud formation or solar radiation, potentially impacting the climate in ways that are still not fully understood or quantified. Suspended particles can then settle back onto the surface through gravitational deposition, or they can be washed down by precipitation. This means that airborne microplastic can be redistributed across the surface, including agricultural fields and water bodies, providing a further entry route into the food chain. In addition to contaminating land and water, these deposited particles can then be re-emitted into the atmosphere at a later stage, entering again the cycle of atmospheric transport.
We have learned in this video that plastics are versatile and ubiquitous, as is plastic pollution. In the case of food production, plastics are essential in modern agriculture, offering important benefits. However, their production, improper disposal, or loss during operations can create serious environmental risks.
To minimize these impacts, responsible and sustainable plastic use is crucial. This includes rational use and changing usage practices, advancements in reuse and recycling, adoption of less toxic and biodegradable materials, education and behavioral change, economic incentives, and legislative enforcement. Since plastic production drives greenhouse gas emissions, we must transition from fossil fuels in polymer production to renewable energy production, ensure a full collection of plastics for reuse, recycling, or upcycling, and use fully biodegradable materials for plastics that can't be collected.
These principles are not only valid for plastics used in agriculture, but for all plastics. There's widespread agreement that tackling plastic pollution requires action across all sectors and needs to include all stakeholders. A binding global plastic treaty is much needed to stop plastic pollution, including a cap on maximum polymer production and regulating harmful plastic additives.